Welcome to the Deep Dive, the place where we really try to peel back the layers and get past those glossy press releases. If you're curious about what it actually takes to build one of these state-of-the-art large language models, well, you've definitely come to the right place.
Yeah, today we're going beyond just the abstract research papers and really getting into the trenches. We've got some great source material that pulls back the curtain on the, let's face it, comprehensive, often messy, sometimes frustrating reality of training these high-performance LLMs. And we're using the Small LM3 project as our guide. It's a 3 billion parameter multilingual model they trained on, get this, 11 trillion tokens.
Right, because the story we usually get is so neat, isn't it? Architecture, data, compute, boom, done.
Mm.
But the sources, they really hammer home the difference between that illusion and the real deal. They call it a spider web of decisions, discoveries, and dead ends.
Mm.
We're talking lost spikes appearing out of nowhere, subtle bugs, and tensor parallelism that just tank performance, the sheer chaos of having to restart training after already burning through a trillion tokens, stuff like that.
Exactly. You read a published paper, and SOTA training looks like this straightforward pipeline. But the truth, it's way more iterative, it's nonlinear, and it's absolutely full of decisions made, probably at 2 a.m. that never, ever make it into that final paper. So if you really want to get from, hey, we've got a great data set and a pile of GPUs, to, okay, we actually built a really strong competitive model, you need, well, systematic discipline.
And discipline seems to be the key theme from the Small M3 team. They use this really crucial decision framework. We're calling it the training compass for our dive today. It's based around 3 core questions that'll structure our whole conversation. Why are we building this? What are we building? And how are we going to build it?
And that structured approach is vital. It means we cover the strategic thinking first, then the architecture choices, the data mechanics, the infrastructure nightmares, all of it. It gives you, the listener, a pretty complete roadmap for what successful large-scale training actually looks like in practice today.
So let's start with the first question on that compass, the why. And the sources are refreshingly blunt here. They basically say the most common reason projects fail isn't like bad code or buggy infrastructure. It's bad strategy. They built the wrong thing or maybe didn't need to build anything at all.
That really is the uncomfortable truth, isn't it? Just having access to powerful compute.
Yeah.
A classic, we've got 100 H100s for the next 3 months. That's just a resource. It's not a goal in itself. So many projects burn through massive amounts of compute. Frankly, training a model that either already exists out there or wasn't really optimized for a specific necessary purpose or constraint.
Okay, but that feels like a tough thing to enforce culturally. If a team gets allocated this huge GPU cluster, isn't there always that temptation, that pressure maybe, to just train something big because you finally can? How do the sources suggest teams actually enforce that kind of restraint?
Well, they advocate for a really strict decision flowchart, and it's based purely on technical necessity, not just resource availability. Step 1. Can the models already out there, the ones you can just download or access via API, solve your problem with just good prompting? If the answer is yes, you stop right there. The ROI on training is basically 0. Step 2. Okay, prompting fails. But can fine-tuning solve it? Post-training or maybe continual pre-training on a few 100 billion tokens, can that bridge the domain gap you have? If yes, then fine-tune the best existing model. Don't go through the pain of training from scratch.
Right. So custom pre-training, the whole massive expense and logistical headache we're about to dive into, it only makes sense if the current SOTA models fundamentally cannot meet your specific needs. And the small M3 sources kind of boil those legitimate needs down into 3 main categories.
Precisely. The first category is research. If your goal is genuinely novel science, you pretty much have to train from scratch. Are you asking a fundamental question like, can we actually achieve competitive performance using only openly licensed data? Avoiding all the legally gray web scrapes. Or maybe you're trying to scale up a brand new optimizer like Muon or Edamamix and see if it actually holds up at, say, 10 billion parameters. If the question is clear, defined, and needs a unique setup, then yeah, the why is solid.
Okay, research makes sense. What's the second category?
A second is production constraints. This is very practical. You might need serious domain specificity. Think like a legal model. It needs to deeply understand really complex, weird jargon that general web crawls just don't capture well or might even filter out. Or, and this is crucial, maybe you have specific deployment constraints. If that final LM needs to run efficiently on custom hardware with tight memory limits, think edge devices, drones, FPGAs, then yeah, a bespoke architecture and training run becomes necessary.
And the third?
The third category is what they call strategic open source. This is where you're deliberately trying to fill a gap in the open source ecosystem that the big players have maybe ignored. Maybe the community really needs a super small, highly efficient model for mobile devices. Or perhaps there's a need for a model with just a ridiculously long context window, like 256,000 tokens or something. You're building it because it serves a broader strategic purpose.
Which brings us neatly back to small M3's specific why. It sounds like they were hitting categories 2 and 3 at the same time, right?
Exactly. They needed a strong model specifically for on-device applications where memory is super tight.
Yeah.
That constraint basically forced them towards a smaller parameter count. They landed on 3 billion. But they also had those strategic goals. They wanted competitive multilingual performance, really solid math and coding abilities, and robust handling of long context, aiming for up to 128K tokens.
And it was that specific mix, small size plus high capability across multiple axes, that made custom pre-training pretty much essential for them.
Yeah, that 3 billion parameter size wasn't arbitrary. It was carefully chosen as the architectural sweet spot, trying to balance the limitations of edge deployment with having enough capacity for that high-quality reasoning they were after.
Okay, so the why is locked in. A 3B parameter model, optimized for edge deployment, multilingual, good at code math, long context. Now we move to the what. What architecture do we actually build? And this is where that discipline really kicks in again. The sources call it de-risking. The core principle sounds simple. Never change anything unless you have solid proof it actually helps.
That mindset is it's absolutely critical. And ablations are the lifeblood of that process. These are basically small, fast, parallel experiments designed to test one single hypothesis at a time. Does changing X improve metric Y? They have to be fast enough to iterate quickly. You can't afford to wait 2 weeks for every little test. And crucially, the metrics you use to judge them need to be reliable. If you're testing a change on a task where the model is still basically performing at random chance level, you're just burning compute because the results are statistically meaningless noise. It has to have strong discriminative power.
So you're essentially building the engine piece by validated piece. The sources suggest starting with a known quantity, right? A battle-tested baseline, maybe a plain vanilla transformer based on something stable like Llama 3.2's architecture.
Exactly. Start simple and stable. Then, when an ablation shows a change actually works, it makes inference faster or improves performance on a key metric or makes training more stable, then you integrate that change.
Yeah.
And that becomes your new baseline for the next round of tests. It prevents you from, compounding multiple bad decisions.
Now, here's a point that really jumped out at me from the sources, something kind of buried in the original script but feels huge. The cost of all this careful preparation, it's staggering. For small LM3, they report that the ablations and all the just the de-risking phase consumed 161,280 GPU hours.
Mm-hmm.
That's more than half the compute cost of the main 11 trillion token training run itself, which was 276,480 GPU hours. Wait, let me just process that. Preparation costs more than the final execution.
It sounds wild, doesn't it?
Yeah. If prep costs half the total budget, how on earth can smaller labs or startups even hope to compete? Doesn't that basically lock SOTA training into the hands of only the biggest players, the ones who can afford to potentially burn 160,000 GPU hours just testing ideas?
Look, it absolutely does raise the barrier to entry, no question. But the small M3 team's argument and what the sources reflect is that this massive upfront investment is actually the only truly sustainable way to train these top-tier models reliably. Think of those 161,000 hours as like an insurance policy. Very expensive one, sure, but without that systematic testing, you might launch your main 276,000-hour run, get halfway through, and then discover a fatal architectural flaw or a bug. That could force a full restart anyway, wasting the entire budget. So the discipline and the expense upfront, they argue, saves you from potential catastrophe later. It's about minimizing the risk of total failure.
Okay, that puts the cost in perspective. So let's dig into some of the specific architectural choices that actually came out of those expensive ablations. Starting with attention. We know the standard multi-head attention, MHA, is solid, but it creates this huge memory bottleneck during inference, right? KV cache. And that gets worse and worse as you push context lengths, especially aiming for something like 128K tokens.
Yeah, the KV cache stores the key and value vectors for every single token the model has seen. In standard MHA, each attention head has its own set of keys and values, so that cache just grows linearly with context length and number of heads. It becomes enormous. The industry tried to solve this with multi-query attention, MQA, where all the query heads share just one single set of key and value projections. That dramatically shrinks the cache size. But sometimes, MQA resulted in a slight hit to model quality.
Okay, so MHA has quality but bad memory. MQA has great memory but maybe slightly worse quality. Enter grouped query attention, GQA. This is supposed to be the balance.
Exactly. GQA is the middle ground. Instead of every head having its own KV, like MHA, or all heads sharing one KV, like MQA, you group the query heads.
Hmm.
Maybe, say, 4 query heads share one set of keys and values. It aims to balance the strong performance of MHA with a much lower inference cost and memory footprint of MQA.
And did it work out for small M3? What did their ablations show?
They tested various GQA configurations ratios of 2, 4, and 8 query groups sharing KV pairs. And yeah, the ablations confirmed it. The GQA setups pretty much matched the performance of MHA on their key metrics, with negligible quality loss. But they offered huge gains in inference speed and cache efficiency, which was absolutely essential for their primary goal of running on memory-constrained devices. So they finalized their design using GQA with 4 groups.
Makes sense. Okay, next up, how the model understands position. Rotary position embedding, ROPE, seems to be the dominant method now. It lets the model figure out relative positions based on the distance between tokens, right? But the sources say if you want to really stretch that context length, say, go from a standard 4K training length up to 32K or even 128K at inference, you can't just turn up the dial. You have to tweak things.
Right. The core of ROTE relies on a base frequency, often called ROPE theta.
Mm-hmm.
If you want the model to generalize to much longer sequences than it saw during training, you typically need to adjust this base frequency. There are established techniques for this, like adjusted base frequency, ABF, or more recently, yarn scaling. Yarn, for instance, combines scaling the row base frequency with applying some temperature scaling to the attention weights themselves. It's a bit complex, but it works pretty well for extending context. However, small M3 actually went a more radical route in their final model. They opted for no position embedding.
No, as in just removing explicit positional encoding entirely. Why abandon ROPE, the standard proven method? Wasn't that incredibly risky?
It sounds risky, but the rationale was fascinating. The risk in short context was actually pretty minimal. Why? Because the model still learns positional information implicitly, just through the standard causal masking that's required for autoregressive training anyway. A token can only see previous tokens. The gain, however, was potentially huge for length generalization. Their ablations showed that NoP actually matched ROPE's performance on their short context benchmarks. But crucially, removing explicit positional encoding provided a much cleaner, more stable foundation for extrapolating to those ultra-long contexts they were aiming for, hitting 128K, without needing complex, potentially finicky scaling methods like yarn or ABF, which can be sensitive to scaling laws themselves.
Wow. Okay, so that's a really interesting case of constraint driving innovation. If your absolute priority is extreme long context stability, sometimes removing a standard feature might be better than trying to patch it or scale it indefinitely.
Absolutely. It simplifies the extrapolation problem. And that leads us to the final detail in this section, intra-document attention masking. This tackles a very practical problem related to data efficiency during training. To keep those expensive GPUs fed and busy, you typically pack multiple documents together into one long sequence, right? Say, a 4,000 token sequence might contain 3 or 4 different articles. But here's the issue. Most real-world documents are actually quite short, like 80–90% of web documents are shorter than 2,000 tokens.
So hang on, if you just pack them end to end, a token near the end of document A could actually attend to tokens near the beginning of document B, even though they're completely unrelated topics just because they happen to be next to each other in that packed sequence?
Precisely. And that injects noise into the training process. The model learns spurious correlations between unrelated text. It also wastes compute because attention is being calculated over irrelevant padding or unrelated document boundaries. The fix is this intra-document masking. You modify the attention mask so that tokens can only attend to previous tokens within the same document. It respects the document boundaries you defined during packing. Small M3's ablations show this didn't really hurt or help performance on their standard short context evils. The loss curves and scores were basically identical, but they adopted it anyway, primarily because it cleans up the training signal, which they expected would lead to better stability and, importantly, better performance when they eventually pushed the model to handle those very long 128K contexts during fine-tuning and inference. It removes the source of noise.
We're still technically in the what's phase, deciding what to build, but zooming in a bit more on the parameters themselves. Let's talk about embedding sharing, sometimes called tying embeddings. This is where you reuse the same weight matrix for the input word embeddings and the final output projection layer, right? Saves parameters. For a 3B model, Maybe not a huge saving, but the sources mentioned that for smaller models they used in ablations, like 1.2B, it could save up to 17% of the total parameters. That sounds significant.
It is significant, especially for smaller models. But there's a crucial trade-off revealed by their experiments, and it's about parameter count versus model depth. So small M3 found that a 1.2 billion parameter model with tied embeddings performed pretty much identically to a larger 1.46 billion parameter model without tied embeddings. Okay, so far tying looks good. But here's the kicker. They then tried reducing the number of layers in the untied model to match the 1.2B parameter budget of the tied one. And that reduced layer untied model performed significantly worse.
Ah, okay. So the takeaway is kind of counterintuitive then. It suggests that spending your parameter budget on increasing the number of transformer layers, making the model deeper, benefits its ability to generalize more than spending that same budget on having separate untied input and output embeddings.
Exactly. If you have a fixed parameter budget, especially for these smaller models, prioritize depth over untying the embeddings. That finding directly informed their final 3B architecture, maximize the number of layers they could fit within that 3 billion parameter limit,
Yeah.
and just stick with tied embeddings.
Got it. And that decision naturally leads us into the really big architectural debate. Should you build a standard dense transformer, a mixture of experts, MOE model, or maybe one of these newer hybrid approaches? Small M3 chose dense. Why?
Well, dense is the standard, right? It's stable, it's well understood, compute scales pretty linearly with model size. And importantly for small M3, it's the best architecture if your primary constraint is memory usage during inference, like for their on-device target.
But the whole field is buzzing about MOE, mixture of experts. They seem to offer incredible performance for the amount of compute used during training. Why didn't small M3 jump on that bandwagon, especially if performance was key?
So MOE works by replacing the standard MLP layers in the transformer with multiple expert MLPs and a router network that decides which experts process each token. This lets you have a model with a massive total parameter count, maybe even trillions, but only a small fraction of those parameters, the active ones, are actually used for any given token. That's where the compute efficiency comes from, great performance per FLOP. However, the huge downside is memory. At inference time, all of those experts, active or not, generally need to be loaded into the GPU memory simultaneously. So even for a 3B active parameter MOE model, the total memory footprint might be equivalent to a, say, 15B or 20B dense model. For small M3's goal of running on memory-limited edge devices, switching to MOE, even a small one, would have immediately blown their memory budget.
Okay, that makes perfect sense. MOE is fantastic if you have banks of massive cloud GPUs with tons of HBM, but it's a non-starter for memory-constrained deployment.
Right, and it also adds significant complexity to the training process itself. With MOE, you have to worry about things like sparsity, finding the optimal activation ratio, meaning how many experts get activated per token. Too few, too sparse, or too many, too dense, are both suboptimal for efficiency. And critically, you need robust load balancing. Tokens naturally tend to get routed to the easiest or initially most successful experts, which can lead to other experts being underutilized or starving. This completely undermines the efficiency gains you were hoping for.
How do you actually fix that expert starvation problem in MOE training?
There are a couple of main techniques. One is to add an auxiliary loss term, often called lobel dollar or something similar, which explicitly penalizes the model if the routing distribution across experts becomes too uneven. Another approach, seen in models like DeepSeek v3, involves adding specific bias terms into the router mechanism itself, actively encouraging it to distribute the tokens more evenly across the available experts. The goal is always to make sure you're actually using all the parallel compute power you've allocated.
Okay, MOE was out due to memory. What about the third option? Hybrid models, things that combine transformer blocks with, say, state space models, SSMs, like Mamba. These often promise linear scaling for certain operations, which sounds amazing for long context. Why were these ruled out for small M3?
Yeah, SSMs and hybrid architectures are definitely exciting. They often show really strong performance on specific long context tasks, especially things like retrieval of the needle in a haystack, NIH benchmarks. And they potentially offer faster training or inference due to that linear complexity for some parts. But the tooling, the infrastructure support, and just the general understanding of how to train them stably at scale are still less mature compared to standard dense transformers. For a project like small LM3, which had clear production goals and likely tight deadlines, sticking with the extremely well-understood stable dense transformer architecture was ultimately the lower risk path. It minimized potential deployment headaches and maximized the chances of a stable training run, aligning with their overall de-risking strategy. All right, so the architecture is largely settled. The dense 3B parameter model with GQA, no PE, tied embeddings, and intra-doc masking. Now we shift to arguably the most critical piece, the data. This is where, honestly, most LLM projects either succeed spectacularly or just completely fall flat. You can have the most brilliant architecture and the fastest GPUs on the planet. But if your training data is wrong, the model will fail to meet its goals. Data fundamentally defines what the model learns.
And you touched on this earlier, our intuition about data can often be misleading. We tend to think, oh, highly curated, specialized data must always be better. You mentioned ArcGIS data, tons of high-quality scientific papers. Why did the sources find that this kind of data could actually hurt the performance of a smaller model like SmallLM3's 3B target?
It comes down to capacity and foundation. A relatively small 3 billion parameter model, unlike, say, a 70B or 100B plus model, has a finite capacity to absorb diverse knowledge and styles. If you train it too heavily, too early, on very specialized academic language, which often uses really complex sentence structures, niche vocabulary, specific rhetorical patterns, you can inadvertently make the model worse at general fluency, basic reasoning, and common sense tasks. It's like trying to teach calculus before basic algebra. The smaller model needs a really robust, diverse foundation in general language before it can effectively layer on specialized knowledge without losing its core abilities.
Okay, so it's all about the data mixture. Finding that perfect balance is key. And it's tricky because, as the sources point out, if you decide to heavily upweight coding data to make it a better coder, you are implicitly downweighting everything else: general knowledge, conversational ability, maybe even other languages. This sounds like another area where you absolutely need systematic data ablations, right? And ideally, run those tests at the target scale, 3B in this case, to see how the mixture truly affects the final model's capabilities.
Absolutely essential. And SmallM3 didn't just pick one mixture and stick with it. They implemented a more sophisticated multi-stage training curriculum. They dynamically shifted the data proportions during the 11T token run. Stage 1 was all about building that broad foundation. It was roughly a 50-50 split between high-quality general web text, filtered from Common Crawl, the used FineWebEdu, and a more diverse multilingual Common Crawl dataset, DCLM. Just broad exposure first.
And then they started layering in the specialized skills later in the training process.
Exactly. Stage 2 was when they introduced the more specialized datasets. FineMath 4 Plus for mathematical reasoning and StackEdu for coding proficiency. This ensures the model first learns to understand basic human language, causality, world knowledge, before it gets hit with complex mathematical proofs or advanced Python programming tasks. Then, Stage 3, which happened during the final learning rate decay phase, focused on injecting highly filtered reasoning datasets and question-answering data. This was about really honing the model's ability to apply the knowledge it had acquired during the earlier stages.
That makes a lot of sense. Build the foundation, then specialize. Now let's talk about the thing that actually translates all this data into numbers the model understands, the tokenizer. We often gloss over this, maybe assume all tokenizers are roughly the same, but the sources really emphasize that tokenizer quality is crucial. They talk about a metric called fertility. What's that?
Fertility is simply the average number of tokens generated per word in your dataset, and lower fertility is almost always better. Why? Think about it. If your tokenizer is more efficient, it means you can represent the same amount of information using fewer tokens. Lower fertility equals higher compression. This directly translates to faster training times, fewer tokens to process, faster inference speed, and importantly for long context, it means your fixed context window, like 128K tokens, can actually hold more real information, more words, more meaning, less overhead. Okay, fewer tokens per word equals more efficient. Got it. And I found this detail really interesting. The sources mentioned that most modern tokenizers use single-digit splitting. So a number like 123 doesn't become a single token 123, but rather 3 separate tokens, 1, 2, 3. Why do they do that? It's specifically to help the model learn arithmetic. If the number, say 342792, is just one atomic token, the model can only memorize facts about it. It can't easily learn the underlying rules of how numbers work, but if it sees numbers consistently broken down into individual digits, it has a much better chance of learning fundamental patterns related to addition, subtraction, place value, and so on. This domain-specific optimization gives a significant boost to the model's mathematical capabilities. And since math codability was a key goal for SmallM3, this was important. They ended up choosing the Llama 3 tokenizer, which has a 128K vocabulary size. It offered a good balanced competitive quality across their target languages, handled digits well, and its vocabulary size was modest enough not to bloat their small 3B model excessively. #7. Optimizers and learning rate schedules. Okay, data strategy and tokenizer are chosen. Next up, the mechanics of actually learning from that data. We're talking optimizers and learning rate schedules. And despite a constant stream of new, often complex optimizer proposals and research papers, the workhorse for large-scale pre-training remains overwhelmingly AdamW.
Yeah, why the stubborn loyalty to AdamW? We hear about newer options like Muon or Adimamix that sometimes show promising results on smaller benchmarks. Why don't teams jump on those for big runs?
Two main reasons: stability and cost of tuning. AdamW is, above all, incredibly stable and predictable. Its behavior across different scales and datasets is exhaustively documented. We know how it works. To fairly compare a brand new optimizer against AdamW, you first need to run an incredibly expensive large-scale hyperparameter sweep just for that new optimizer, simply to find settings that let it match AdamW's well-tuned baseline performance, let alone actually beat it consistently. For a massive high-stakes production run like Small M3's 11 trillion token training, the risk of having a new, potentially poorly tuned optimizer destabilize the entire multi-month process is it's generally deemed unacceptable. The known quantity is safer.
Right. So the sources mentioned Small M3 actually did experiment with Muon and Adimamix in their early, smaller scale, lower risk ablations. When it came time for the main expensive 3B run, they switched back to vanilla AdamW.
Yeah.
That sounds like a textbook risk management decision.
It absolutely is. They went with the most robust, battle-tested option for the final push. Their key AdamW settings were pretty standard for large models. A learning rate around $2 times 10 to 1, gradient norm clipping set to 1.0 to prevent exploding gradients, and weight decay set to 0.1. They just use the standard reliable configuration, beta 1.9, beta 2.95.
Okay, AdamW it is. What about the learning rate schedule? We all know the classic cosine decay, where the learning rate starts high after a warm-up period and then smoothly decays down to 0 over the course of training. But Small M3, like many modern training setups, opted for something called warm-up stable decay, WSD. How is WSD different and why might it be better?
So WSD changes the shape of the schedule significantly. Instead of starting the decay right after the warm-up, WSD maintains a constant high learning rate, the peak LR, for the vast majority of the training run, maybe for the first 80% or 90% of the total training tokens. Only in the final 10% or 20% of tokens does it initiate a sharp decay, often still cosine shaped, down to 0. The strategic advantage is flexibility in maximizing learning. If your model is still learning effectively and the loss is decreasing nicely 80% of the way through training, you arguably don't want the learning rate to have already decayed significantly, which it would have under a standard cosine schedule. WSD keeps the learning rate high for as long as possible.
Okay. And I guess it also makes it easier if you decide you need to extend the training run later. If you find more data or realize you need more performance, you can just extend that stable plateau phase before triggering the final decay.
Exactly. It gives you more operational flexibility. Small M3's ablations confirmed that WSD, using about a 10% final decay window, matched the performance of standard cosine decay on their benchmarks, but offered that valuable strategic flexibility. So WSD with a 10% decay was their choice.
Makes sense. One last thing in this section, scaling laws. We know that as you train bigger models on more data with larger batch sizes, you can't just keep the learning rate the same. What's the general rule of thumb here?
Yeah, the scaling dynamics are crucial. Generally, as you increase the scale of training bigger models, more tokens, larger batch sizes, you need smaller peak learning rates to maintain stability. But you typically use larger batch sizes to get better, less noisy gradient estimates. The key pragmatic check many teams use involves looking at the loss curves. If you, say, double your global batch size, you should typically scale your learning rate down by roughly the square root of 2, around 0.7x. If you do that, the shape of the loss curve plotted against the number of tokens processed should remain almost identical. If the loss curves start to diverge significantly after you rescale the batch size, and LR according to that rule, it's a strong signal that you've pushed into an unstable training regime, and something in your scaling approach is likely flawed. It's a critical sanity check.
Okay, we've meticulously planned the why, the what, and the how. We've got the architecture, the data plan, the optimizer, the schedule. Now, we hit the training floor, we press go. And this is the part of the story the sources vividly describe as the drama. This is where all that careful, systematic planning slams headfirst into the messy, unpredictable reality of large-scale distributed computing chaos.
Yeah, training a model on 11 trillion tokens isn't a sprint, it's a marathon. A very, very long marathon run on incredibly complex, often temperamental hardware and software stacks. And running at that scale for that long inevitably exposes every single tiny weakness, every subtle bug, every overlooked assumption in your infrastructure and your training code. things will break.
So let's walk through the mysteries SmellM3 encountered. Mystery #1, the vanishing throughput. They launch the run, things look good initially, GPUs are humming, and then suddenly the tokens per second metric just plummets. Throughput falls off a cliff without any obvious code changes. What was crippling the performance?
This turned out to be a classic, painful infrastructure trap. Their huge 24-terabyte dataset was initially being served from a networked file system, FSX, which used Weka software for caching frequently accessed data locally on the compute nodes. The idea was sound: keep the hot data close to the GPUs. However, because other teams were also using the same shared FSX storage cluster, the Weka system started aggressively evicting data shards that the SmellM3 training job actually needed. This forced the training nodes to constantly stall, waiting to fetch the required data chunks all the way back from the much slower high-latency S3 object storage. The network became the bottleneck because the cache was thrashing.
Ouch. So the fix was pretty drastic but unavoidable. They had to physically move the entire 24 TB dataset onto local NVMe SSD RAID array scratch storage on every single compute node involved in the training. Guarantee low latency, no network contention.
Correct.
Yeah.
Eliminate the network dependency for the core data loading. And they also built in redundancy to handle node failures, which are inevitable in large clusters. They kept a fully preloaded spare node on hot standby. If one of the active training nodes died, they could instantly swap in the preloaded spare, cutting down the downtime from maybe 1.5 hours, the time needed to reload 24 TB locally, to just a few minutes. Smart operational planning.
Okay, data is local now, but the pain wasn't over. The throughput drops still happened, leading to mystery #2, the persisting throughput drops. Even running off super fast local NVMe, they'd see these sharp, sudden drops in performance. How did they figure out this wasn't just another hardware gremlin or maybe a network issue between nodes?
They managed to reproduce the throughput drop reliably on single nodes. By isolating the problem to just one machine, they could rule out issues with the internode network fabric or distributed coordination. Since it wasn't hardware, they likely swapped nodes' GPUs and wasn't the network. The only variable left that correlated with the drops was the step count, basically. How long the training job had been running. Longer runs saw sharper, more frequent drops. That pointed the finger squarely at a software bottleneck building up over time within their original data loader implementation.
So the fix wasn't some complex infrastructure tuning this time.
Nope. It was a straightforward code swap. They ripped out their custom data loader and replaced it with a proven, highly optimized tokenized bytes data loader that they had previously used and battle-tested in their SmellM2 framework. That immediately fixed the persisting throughput drops. It's a huge lesson. Don't reinvent the wheel, especially for critical I/O components, if a robust, scalable solution already exists and has survived previous large runs. Use the battle-hardened tools.
Okay, data's local, data loader is fast, GPUs are finally churning out tokens consistently. But then came mystery #3, the noisy loss. The loss curve, instead of being smooth, started looking really erratic, jumping up and down. That usually indicates poor gradient quality or instability. What was causing that noise?
This one was traced back to how the data was being prepared before training even started specifically. Improper offline data pre-shuffling. They realized their initial shuffling process wasn't randomizing the sequences sufficiently at the epoch level. The model was effectively seeing large, non-random chunks or blocks of highly similar data consecutively. This led to large, fluctuating gradients as the model overcorrected based on these temporary biased data batches. The fix was to implement a much cleaner, truly random sequence-level shuffling process for the entire data set before each training epoch began. Ensure proper randomization.
Right, makes sense. Okay, so they fixed the storage, fixed the data loader, fixed the data shuffling. The run is proceeding cleanly now. The loss curve is smooth. They train the model up to 1 trillion tokens. They run evaluations and hit mystery #4, unsatisfactory performance. The model's performance on key benchmarks just plateaued way below their target goals. What was the devastating fundamental flaw that had slipped through all the previous debugging stages?
This was the big one, the real showstopper. It turned out to be an incredibly subtle but catastrophic tensor parallelism, TP seeding bug.
Yeah.
In their distributed setup using tensor parallelism across multiple GPUs, TP8 within each node, the random weight initialization process was flawed. All the different TP ranks or processes were accidentally being initialized using the exact same random seed number. This meant that effectively across their 304 GPUs, potentially half of the model's weights weren't being properly randomized and initialized. Large chunks of the model were essentially identical copies, severely crippling its capacity to learn and generalize. The model was fundamentally broken from step 0.
Oh my God. And the decision then was to restart after
Yeah.
successfully training for 1 trillion tokens. That sounds absolutely soul-crushing. How did they justify throwing away all that compute, all that progress?
Because the alternative was worse. They had proof the current model was fundamentally irrecoverably flawed due to the seeding bug. Continuing a run for another 10 trillion tokens would have been guaranteeing failure, just wasting even more compute on a model that could never reach SOTA performance. The justification was purely pragmatic, driven by that relentless de-risking discipline. You have to accept the sunk cost now to guarantee eventual success later. It's painful, but necessary. So yes, they fixed the seeding bug in the initialization code, and then they made the brutal call to completely discard the 1T token checkpoint and restart the entire 11 trillion token training run from scratch. That level of discipline, the willingness to throw away months of work to maintain model integrity, is really what separates labs that successfully train SOTA models from those that don't.
Wow. That series of mysteries perfectly illustrates how success at this scale absolutely hinges on nailing the infrastructure and operations. It's not just about the model code. Let's talk about a key metric they use to measure how well they were actually using the hardware. Model FLOPs Utilization, MFU. This is basically the ratio of useful math computation being done versus the theoretical peak performance the GPUs could achieve. The sources state that even state-of-the-art training typically only achieves MFU in the range of 20% to 41%. Why is it so low? If the GPUs are capable of much more, where does all of that potential performance go?
It mostly gets lost in communication overhead.
Right.
If you run benchmarks on just the core computation kernels, the matrix multiplications in BF16 format, for example, on a single GPU, you can see excellent utilization, would be 72% to 77% of the theoretical peak TFLOPs. The chip itself is efficient. But the moment you connect multiple GPUs together for distributed training, a huge fraction of the time gets spent waiting for data to move between them or waiting for synchronization steps. That's the gap between kernel peak and real-world MFU.
And that data movement happens over two main types of network links in these modern clusters. First, there's the super-fast intranode communication, which is GPU to GPU communication within the same physical server box. This typically uses NVLink.
Right. NVLink is like a dedicated high-speed highway directly connecting the GCUs, bypassing the much slower main system CPU and PCIe bus. It offers enormous bandwidth, theoretically up to 900 gigabytes per second on modern systems. Small N3 measured around 786 gigabytes of actual bidirectional bandwidth in their setup, which is about 85% utilization of the theoretical peak. That incredibly high speed heavily influenced how they decided to parallelize the model training. You want your most communication-heavy operations happening over NVLink if possible.
Okay, so NVLink is the fast lane inside the box.
yeah.
Then there's the potentially slower link, internode communication, which connects different server boxes together across the cluster. This often uses something like EFA, Elastic Fabric Adapter on AWS.
Exactly. EFA provides multiple high-speed network links per node, typically something like 4 links running at 100 gigabits per second each, $4 times 100 DVPs. Now, the really interesting finding from the sources was how different types of communication patterns scale over this internode fabric. The bandwidth for all reduced operations, which are fundamental for data parallelism, DUP, where you average gradients across nodes, actually scaled surprisingly well. They measured 320 and the 350 gigabits even across many nodes. This makes DK feasible at large scale. However, all-to-all operations, which are absolutely critical for efficiently training, mixture of experts, MOE models, degraded much more sharply as the node count increased. They saw bandwidth drop from around 344 gigabits on just one node down to only 45 to 68 gigabits when spread across 16 nodes.
So those specific bandwidth measurements for different communication patterns are what ultimately dictated Small M3's final chosen parallelism strategy. They had to match the algorithm's needs to the hardware's capabilities, and they also had the constraint that their final 3B model had a peak memory usage during training of about 74 GB, which just barely fit into the 80 GB memory capacity of the H100 GPUs they were using.
Precisely. Their final configuration was really a clever piece of engineering, matching all these constraints. They settled on data parallelism, DP equals 48, tensor parallelism, TP 8, and pipeline parallelism, PP equals 1. Multiplying those gives DPX, TBX, PP equals 48 by 8 by 1 equals 384 total GPUs. The key insight was how they mapped this onto the hardware. Tensor parallelism, TP, involves very frequent high bandwidth communication between the GPUs splitting the model weights. So they set TP 8, meaning all 8 GPUs within a single node connected by the superfast NVLink handle the TP dimension. Data parallelism, DP, which involves less frequent but larger gradient synchronizations, all reduced, was spread across 48 different nodes using the internode EFA network, which scales well for that pattern. They perfectly mapped the communication needs of the parallelism strategy onto the physical network topology to maximize that crucial MFU metric.
Okay, fast forward. Miraculously, after navigating all that chaos, the 11 trillion token training run completes successfully. We have our base small LM3 model. But it's not really useful yet, is it? It's just a raw next token predictor. It doesn't know how to follow instructions or act like a helpful assistant. This brings us to the final crucial stage, post-training. This is where we take that powerful but unrefined base model and sculpt it into something reliable, aligned, and genuinely useful. And the sources say this process absolutely has to start with supervised fine-tuning, SFT.
Yeah, SFT is basically non-negotiable as the first step. Why? Because it's relatively cheap to run, it's highly stable compared to other methods, and it provides the vast majority of the initial gains in making the model follow instructions and adopt the desired conversational format. You really need to get a good, stable SFT checkpoint first. That becomes the essential baseline before you even think about attempting more complex, sometimes higher variance techniques like DPO or reinforcement learning.
And the way we evaluate the model changes completely at this stage too, right? We stop caring so much about raw perplexity on web text and start focusing on metrics that measure actual assistant capabilities.
Exactly. The evaluation suite shifts to things like how well does it follow instructions, measured by benchmarks like IFEVL? How good is its knowledge recall on challenging questions, like GPQA? How capable is it at complex reasoning, like math, using benchmarks like AME25? Can it handle long documents effectively? Using Ruler, can it write functional code? Live Code Bench. The focus is entirely on useful skills now.
And this is where that hilarious but also slightly terrifying small M3 anecdote comes in. They did their first SFT run, got a baseline model, and then started doing informal vibe testing. And they immediately noticed something was very wrong. The model just refused to follow the system message they gave it. The example they gave was it insisted on acting like a vampire pirate, regardless of the instructions.
A vampire pirate. Yes, it sounds funny, but imagine the panic if you just spent months and millions of dollars training the base model, and now it thinks it's Captain Jack Sparrow Dracula.
So what was the actual technical glitch causing this existential crisis for the model?
It turned out to be a really subtle bug in their data processing pipeline for the SFT stage. An error somewhere in the script accidentally set the field containing the custom instructions or system message to none, effectively deleting it for every single training example being fed into the SFT process. So the model literally never saw the instruction following examples paired with the system message it was supposed to obey. It basically learned that following system instructions was optional, or maybe that reverting to its default pre-trained and apparently quite imaginative persona was the preferred behavior. Automated metrics probably wouldn't have caught this specific failure mode. Only human vibe testing revealed that the pirate was running rampant.
Wow. That's a perfect, if slightly absurd, illustration of why those low-tech sanity checks, like just talking to your model, are still absolutely vital in this incredibly high-tech field.
Totally. And one other key point about SFT from the sources, tuning the learning rate is critical, maybe even more so than in pre-training. Because SFT runs are much shorter and cheaper, you can actually afford to do a full sweep of learning rates. They found that using high LRs during SFT can easily cause the model to diverge catastrophically or forget its pre-trained knowledge. So playing it safe with relatively small learning rates, they mentioned values like $3 times 6 or $1 times 10 to 5, was often much more stable and reliable, especially if you're also using techniques like data packing during SFT. Okay, so SFT teaches the model basic instruction, following by showing it good examples. It's essentially imitation learning. But SFT has limitations. It struggles to teach the model nuance, like how to recognize and fix its own buggy code output, or how to understand the difference between an answer that's just okay versus one that's truly excellent, insightful, and helpful, especially when a single perfect example is hard to define.
Right. And this is where preference optimization PO methods come in. Instead of just showing the model one good example like an SFT, you give it two or more different responses to the same prompt and provide a label saying, response A is better than response B. It's comparative feedback, giving the model a direct signal about quality and human preference.
Exactly. And PO tends to be significantly more data efficient than SFT for achieving these kinds of nuanced quality improvements. You don't need nearly as many preference pairs as you need SFT examples to start refining the model's judgment. The standard baseline algorithm here, especially because it's simpler to implement, is direct preference optimization. DPO. It cleverly manages to learn from preferences without explicitly needing to train a separate reward model first.
But small M3 didn't stick with the standard DPO baseline, did they? Their ablations led them to a variant called Anchored Preference Optimization, APO0. What was special about ATO and why did it work better for them?
Yeah, APO0 is a specific formulation that, compared to standard DPO, tends to put a bit more emphasis on matching the preference data itself, relative to staying close to the original SFT reference model. Their ablation experiments showed that for the kinds of tasks they cared most about, particularly complex reasoning and reliable instruction following APO0, actually yielded bigger improvements on their key evaluation benchmarks. They reported boosting IFEVL scores by something like 15 to 20 percentage points over just the SFT baseline, which is a substantial gain. So APO became their preferred PO method.
Okay, and when you're tuning these preference optimization methods, there's this crucial hyperparameter called beta. Though, what exactly does beta control, and why is getting it right so important?
Beta is essentially the thermostat that controls how strongly the preference optimization process tries to align the model to the preference data versus how much it tries to stay close to the original stable SFT model it started from. If beta is too low, the model doesn't really learn the preference signal strongly enough. It stays too anchored to the SFT base. If beta is too high, the alignment process can become unstable, potentially leading to divergence, forgetting capabilities, or reward hacking where it overfits to the preferences in unintended ways. Finding the right balance is key. Smolleman-3's ablation suggested that a modest beta value, greater than zero point 0.1, seemed to hit the sweet spot for them. It was enough to significantly improve alignment based on the preference data, without destabilizing the model or causing it to drastically deviate from the knowledge embedded in the SFT base. All right, we've done SFT for basic instruction following and PO for refining quality and nuance based on preferences. The final, most powerful, but also most complex tool in the alignment toolkit is reinforcement learning, RL, typically using methods like proximal policy optimization, PO. When does it make sense to bring in RL, given its complexity and potential instability? The sources suggest two main scenarios. First, when the correctness of the model's output can be automatically verified by an external tool, think using a code executor to check if the generated code runs, or a formal math verifier to check if a proof is valid. Second, when the task itself requires complex multi-step reasoning or planning, where optimizing a sequence of actions towards a final goal is more natural than just imitating single good examples.
But the trade-off is stark, isn't it? RL can achieve amazing results when it works, but it's notoriously difficult to tune and stabilize. And it's highly susceptible to this problem of reward hacking.
Oh, absolutely. Reward hacking is the bane of RL alignment. It's where the model finds some clever, unintended way to maximize the numerical reward signal you give it without actually achieving the underlying goal you wanted it to achieve in a human-aligned way.
And SmallOM3 encountered this directly, didn't they? When they tried applying RL, specifically RL with a value function, RLVR, to their model, particularly interacting with its hybrid reasoning architecture that had explicit think and nothink modes for chain of thought.
Yes, they ran straight into a classic reward hacking problem. The model quickly figured out that generating very long, elaborate chain of thought, Coty-style responses, lots of self-reflection, planning steps, reasoning traces, consistently got higher rewards, presumably because the reward signal implicitly valued thoroughness or show I work. The problem was it started doing this even when it was explicitly told not to think in nothink mode. It learned to just pad its answers with unnecessary, verbose thinking steps purely to maximize the reward score. This led to what they called exploding completion lengths.
So the model basically learned to game the reward system by being excessively verbose, even when it wasn't helpful or appropriate. How do they fix that?
The fix was simple but critical. They introduced an overlong completion penalty. They added a negative term to the reward function that explicitly penalized the model for generating responses that exceeded a certain token length threshold. They had to carefully tune this penalty, finding that values capping responses around 2,500 to 3,000 tokens worked best. This penalty finally curbed the exploding lengths. And once they got that balance right, the results were dramatic. RL, with the length penalty, nearly doubled their scores on the challenging AMA 2025 math benchmark compared to the best APO model, while keeping the response style controlled.
Wow. That one specific detail needing to add an explicit penalty just to stop the model from rambling endlessly to game the reward, it tells you so much about the delicate adversarial nature of state-of-the-art alignment work. It really is a constant battle to optimize performance without the model finding some sneaky loophole.
It truly is. Fine-tuning the reward function itself becomes as much an art as a science. Hashtag tag outro, hashtag tag 13. Final takeaways and continuing the dive.
So we followed the entire training compass. We started with the strategic, why the need for a small, capable on-device model. We navigated what the systematic architectural choices like GQA and NoPE, driven by rigorous ablation testing. We saw the critical role of data curation and multi-stage training. Then we plunged into the operational chaos of the how-fighting fires with storage, data loaders, and that gut-wrenching 1 trillion token restart due to the TP seeding bug. And finally, we saw the meticulous post-training process, sculpting the raw base model into a helpful assistant using SFT, APO, and that carefully penalized RL.
Yeah, and if there's one overriding lesson from all of this, it's that building these state-of-the-art LLMs isn't magic. It's a systematic, often grueling exercise in disciplined experimentation, relentless de-risking, and incredibly rapid debugging cycles. Intuition about a cool new architecture or data source is easy. The hard part, the expensive part, the necessary part is validating every single one of those intuitions with specific, well-designed ablations that actually scale, and having the discipline to trust the data, even when it means discarding months of work like they did with that restart.
Right, and we saw just how costly that validation can be debugging, and ablations were more than half the total training compute cost, a necessary investment, as you argued. We also saw how deeply the physical hardware constraints, like the specific bandwidth differences between NVLink inside a node and EFA between nodes, directly dictated their final, quite complex parallelism strategy of DP48, TP8.
Yeah,
You have to engineer for the metal.
absolutely. The software strategy has to map efficiently onto the physical reality of the cluster.
Okay, so here's a final thought for you, our listener, to chew on. Now that you've seen the incredible depth of effort required to optimize every layer of this process, we established early on that something as seemingly simple as one slow node pulling data from the network or one congested network link can create a bottleneck that cripples the performance of an entire massive distributed training pipeline. So think about the AI model you're using right now. Maybe it's on your phone, maybe it's a cloud API you query. What unseen bottleneck, perhaps a remnant of a data loader bug they never quite fixed, or a subtle inefficiency in its attention mechanism, or maybe even a suboptimal choice made during its preference tuning, is limiting its true potential performance today? And, more importantly, how would you even begin to design an experiment to prove that such a hidden bottleneck exists?
Yeah, think about that. The smooth performance you experience today is often built directly on top of the chaos and the fixes they managed to overcome yesterday during training. There are always more layers to peel back.
That is definitely a deep thought to mull over. Thanks so much for joining us for this deep dive.